guys, it's Miss Maneely, and I'm going to go ahead and teach the lesson on chapter 10.2, and this is inference for comparing two population means. So we're going to be looking at the sampling distribution for the difference between two means. We're going to be looking at confidence intervals as well as tests of significance. We're also going to look at a special case of matched pairs, which is actually something that's included in chapter 9. But I feel like it doesn't really make sense until you look at situations where we're looking at two different groups. So when we get to a problem like that, I'll show you what I mean. You'll find that the inference procedures for two means are very, very similar to the ones excuse me, the ones that we did with two proportions. Obviously, the formulas are a little bit different, and some of the conditions are different as well. But our objectives are the same. We want to first talk about the sampling distribution, because the sampling distribution, whether or not it's going to be a normal distribution or a t-distribution, is going to determine how we construct our confidence interval. It's also going to help us find the p-value if we're doing a test of significance. And so we're going to talk about when it's appropriate to use those two procedures and any other special cases that apply when we're dealing with two means. Okay, so I showed you a slide like this when we were looking at situations involving two different population proportions. If we're dealing with two populations and we want to compare the means, I just wanted to just differentiate the notation that we use. Again, if we're dealing with means, then the population parameter is going to be the Greek letter mu, and our sample statistic is going to be x bar. And then n represents the sample size. And notice that we use subscripts to differentiate between the two groups. You can use numbers if you want, or if you're talking about the mean difference between males and females, you can use like m and f for those subscripts. Treatment versus control, t and c, whichever subscripts are appropriate for the situation. If you are going to use 1 and 2 or subscripts that aren't like obvious, then you want to make sure that you define them somewhere in the problem so that whoever's reading your response understands which way you're subtracting. Okay, when we're talking about two sample hypothesis tests for means, we want to make sure that the information that we're getting, the data that we're getting, is being selected randomly and also independently. This is very important. Anytime you're dealing with two sample procedures, the two samples must be independent. And so that's an added condition that we didn't have when we were just dealing with single means or single proportions. But that is required in order for us to do statistical significance, or inference, I'm sorry. All right, so when we're, just like when we were setting up hypothesis tests for proportions or difference between two proportions or single means, you always have your null and alternative hypothesis. When we're comparing two population proportions or means, we're always looking at the null hypothesis being that there is no difference between the two groups. So it helps sometimes just to say, okay, so that means if there's no difference between the two groups, that mu sub 1 is equal to mu sub 2, or if we're dealing with proportions, p sub 1 is equal to p sub 2. But once we start getting into like the mechanics of the problem, we're ultimately subtracting the two. So if you think about subtracting mu sub 2 from both sides of this equation, you end up with mu sub 1 minus mu sub 2 is equal to 0. So you can either describe your null hypothesis this way, where you're setting the two equal to each other, or you can describe your null hypothesis as the difference between two means being equal to 0. Like I said, this is the method that I prefer because it's consistent with the mechanics of the problem once we start getting into the probability statement and the work that you need to show. But actually they're equivalent, so you can set up your hypothesis either way. Your alternative hypothesis, again, is going to be based on the context of the problem, whichever is appropriate. If you're just looking to see if there was a change from one year to a next, then you're going to want to do a two-tailed situation. If you're thinking that one year was higher than the other or lower than the other, then you're going to be doing a one-tailed, lower or higher. Now the one thing to keep in mind is it doesn't matter which way you subtract. So for example, if I wanted to look at this alternative, I could actually look at it this way, where I'm doing mu 2 minus mu 1, but if I were to subtract this way, I'd actually be expecting that the difference was greater than 0. So it doesn't matter which way you subtract. You just want to make sure that you're consistent with your problem throughout the problem and that you're subtracting in the same way each time. So your test statistic may be a different sign than the one that I get, but our p-value should ultimately be the same. So it doesn't matter the order of your subtraction. Okay, the second step obviously is to verify our conditions. This is the planning phase. Sorry, the last stage was the state. Okay, and then we move to our planning phase, and this is where we verify all the conditions. And we still have the same conditions that we've always had. Our samples must be random. Our populations must be at least 10 times the size of our samples. And then the normal condition, remember, with means is a little bit different than it is with proportions. This is where either it tells you in the problem or it's an appropriate assumption to make that the population distribution is normal. If it doesn't tell you in the problem, then you want to look to see if your sample is large enough. So both samples in this case, if I'm dealing with 2, would have to be larger than 30 for me to say that the normal condition is met. If, for example, I'm stuck in a situation where I'm not told anything about the populations, my samples are small, but I'm given data, then you would want to plot the data if you're and you'd want to do 2 different plots. Okay, so that would be your OR. Okay, so if you're given data and not any information about the distribution, then you're going to want to plot the data. Usually I use a normal probability plot, just because it's faster to draw on my paper than it is a histogram. And again, you're doing it for both sets of data. So you'd have to draw 2 different plots. And again, when you're doing a plot, you want to make sure that you're describing what it is that the audience is looking at. You're not just going to put dots on a paper and assume that the audience understands what it means. You need to interpret that graph and say, since both distributions, these are normal probability plots, both indicating that the sample data is distributed approximately normally. The only other condition that is new is this independence. If we're looking at 2 completely different groups, the groups must be independent. And that is required for any of our 2 sample procedures. Okay. The third step would be the mechanics of the problem, and obviously you need to determine which distribution you're going to be using. Just like before with means, we can use a Z distribution or a T distribution, and it's going to depend completely on whether or not the standard deviations of the populations are known. So we use a standard normal distribution or a Z-test if the population standard deviations are given to you. So you're always going to have a standard deviation to work with, whether or not it's coming from the population or the sample will determine which test you use. So if it's coming from the population, you want to make sure you use a Z-test. If you're only given the sample data and your standard deviations are coming from that, you want to use a T distribution. And just be careful with the T distribution, you must also describe your degrees of freedom. Now in this case, remember we said degrees of freedom is always n minus 1. Well, in this case, I have 2 sets of data, so which degrees of freedom do I use? There's a rule of thumb that tells us to go ahead and use the lesser of the degrees of freedom. So if your samples are different sizes, you would just refer to the smaller sample size. There's also another complex algorithm that you're not expected to know that your calculator uses. So if you are doing the test on a calculator, the calculator will spit out degrees of freedom for you. And it'll probably be some decimal number, and you just want to make sure that you're writing that on your paper so whoever's grading your exam knows what degrees of freedom were used to calculate the probability. And we're going to do an example like this, so you'll see what I mean when we look at the calculator. All right, so in terms of the sampling distribution for the difference between 2 sample means, this was kind of where we started. This would correspond to what we did in Chapter 7 for individual one sampling situations. And we did this also at the beginning of Chapter 10 with proportions. Obviously, we're looking at independent simple random samples from 2 different groups. The mean of our sampling distribution is just going to be the difference in my population means. And so what that would look like is the mean of x bar sub 1 minus x bar sub 2 is equal to mu1 minus mu2. And if I'm doing the standard deviation of x bar sub 1 minus x bar sub 2, remember the standard deviation is just going to be the square root of the sum of the variances. Well, if I'm dealing with a standard normal distribution, if I'm given the population standard deviations, then I'm going to have my variance of population 1 over n1 plus my variation of, or my variance of population 2 over n2. These formulas are things that are on the formula sheet. You're not expected to memorize them. And then the shape of the distribution will be normal, as long as the normal condition is met. Either it tells you in the problem that both distributions are normal in terms of the population, the samples are large, or you have looked at the data and can tell that the data is distributed approximately normally. So those are your sampling distributions. If you're actually looking at a graph, this would be a normal distribution for your x bar 1 minus x bar 2. If you're stuck in a situation where you don't have the standard deviations of the populations, then you're stuck using your sample standard deviations. In a situation like that, then we're no longer using a standard normal distribution. This is called our standard error, and we must use a t-distribution. Oops. Okay, and again, your calculator will tell you the degrees of freedom that you would use in such a distribution. Anytime you're doing a significance test, you must show your work. So for example, if I were looking at my do phase where I'm showing the probability, I'd have the probability that the difference in my x bars is greater than some number. When you're doing this step on the calculator, you will have to physically do this calculation by hand. And what I mean by that, I mean, you'll obviously probably use your calculator to subtract, but your calculator doesn't spit out that number. The next thing you would write then in your do phase would be the probability of your z-score being greater than some number, or a t-score if you're using a t-distribution. Your calculator will give you this number. And your calculator will give you the p-value as well. So if I said equals p-value, your calculator will spit those out when you do the test using the test command on the calculator. The only thing that you will see on the calculator is it'll ask you about pooling. Pooling is only used in significance tests. So your calculator does pool whenever you're doing a test of significance for proportions. You just don't realize it. But what we want to make sure that we understand is that the reason we pool is in our null hypothesis, for proportions anyway, we're basically saying that we're assuming the two population proportions are the same. So if the two population proportions are the same, then I'm saying that there's really no difference between these two populations. So if I take two samples, so let's say I have in sample 1, there's 12 out of 50. So let's say this is my p hat sub 1. And then let's say in my p hat sub 2, I have 10 out of 50. Well, if my null hypothesis is saying that there is no difference between the two groups, then what I would do is I would pool my proportions, and I would take all of the successes, and I would add up my two samples. And so it would be the same as having 22 out of 100. This is what we call the pooled proportion. And like I said, your calculator automatically does it when it's calculating a z statistic in the calculator. Whenever you're doing a test of significance. With means, however, when we have a null hypothesis that says that mu1 is equal to mu2, I can't say that my x bars, that there's no difference between my samples unless I know something about the standard deviations. The standard deviations would have to be the same as well for me to say that the two distributions are the same. So what it boils down to is that we do not pool when we're dealing with means. We do pool when we're dealing with proportions. And like I said, your calculator does it automatically with proportions, but with means it will ask you, and you always want to answer no. Okay. You'll get your p-value, and then you'll state your conclusions like we always have. Is the result significant? Can we reject the null hypothesis? And then make sure not only that you're interpreting the decision in the context of the problem, but that you always refer back to your alternative hypothesis. Okay. Let's do an example. So in number 1, it says, based on information from the U.S. National Health and Nutrition Examination Survey, the heights in inches of 10-year-old girls follow a normal distribution. The heights of 10-year-old boys also follow a normal distribution. It's a little bit different. Suppose we take independent SRSs of 12 girls and 8 boys of this age and measure their heights. If the mean height for girls in the sample is 57.2 inches and the mean height for boys in the sample is 55.4 inches, is the difference between the heights significant? Perform an appropriate test and state your conclusions. I'm going to break this down in a couple of different ways. First, I want to talk about the sampling distributions. Let's jot down what we know about these distributions. For girls, I'm going to just use the letter G to represent girls. We are given are distributed normally with a mean of 56.4 and a standard deviation of 2.7. This is my mu sub G and my sigma sub G. For boys, I'm told they are also normal with a mean of 55.7 and a standard deviation of 3.8. And again, this would be my mu sub B. This is sigma sub B. So the fact that we are given the population standard deviations is a quick clue to me that I'm ultimately going to be using a T distribution. I'm sorry, a Z distribution. I don't know why I did that, sorry. Okay, so right away I know, because I'm given the population standard deviations, that I can use a Z distribution. So let's first think about the distribution. If we're looking at the difference between girls and boys, it doesn't matter how you want to subtract. I'm going to do girls minus boys. So let's say I'm looking at the sampling distribution of X bar sub G minus X bar sub B. And I want to talk about the shape, the center, and the spread. I know that the shape is normal because I am told that both populations are normal. And that's exactly what I'm going to write. Okay, the center of my distribution. So now I want to figure out the mean of X bar sub G minus X bar sub B. And the reason that my subscripts have the X bars is because it's my samples that are going to vary. Every time I take a sample of girls and boys and subtract the means, I'm going to get a different value. And all those values are going to vary according to a normal distribution. The center of that distribution is simply going to be the difference in the means of my populations. So it's going to be the mean of the girls, 56.4, minus the mean of the boys, 55.7. And that is going to be, let's see, 56.4 minus 55.7. Okay, and I get 0.7. So that's the mean of my sampling distribution. Shoot. Okay, if I want to know the spread, then this is where I'm going to use that standard deviation formula. So the standard deviation of X bar sub G minus X bar sub B is going to be the square root of the sum of my variances. So the variances, remember, are going to be the standard deviation squared. So I'm looking at 2.7 squared over my sample size. And I think, does it tell us the sample size of the girls? So I know that for girls, N was 12, and for boys, N was 8. So notice that I have really, really small samples. If I didn't know that the populations were normal, I would not be able to proceed unless I was able to plot that data if I had the data available. So when I'm computing the standard deviations, again, I'm going to take the variance of the girls, which is going to be 2.7 squared divided by 12, plus the variance of the boys, which is going to be 3.8 squared over 8. And again, these are just, let me go back to that slide with those formulas on it. Okay, that's what I circled here, the variances. The means are here. And remember, with standard deviation, we always add the variances. Okay. And so that Move that out of the way. Okay, so when I do that computation, be careful when you're doing this to put your fractions in parentheses. So I've got 2.7. I want to square that before dividing by the 12. I'm going to close that set of parentheses, and then I'm going to add that to 3.8 squared divided by 8. All right, and so this will give me the standard deviation of my sampling distribution, 1.553. Okay, so I'm going to hold on to this for a minute, and I'm going to show you when we go to do our test of significance, there are going to be two ways that you could actually do the test. You could compute the probability using the sampling distribution, and hopefully it'll all work out, or you can compute the probability looking at using the test command on your calculator. So right now, I've just stated the sampling distribution. If I want to now do an appropriate test, I've got to do my 4 stages, where let's talk about my state. This is where I'm going to state my hypotheses. So the null hypothesis is basically going to be that there is no difference between the two means. And again, I'm using my population notation. The mean of the girls minus the mean of the boys would equal 0. And I am just looking to see if there is a difference between the girls' and boys' heights. I'm not looking to see if one is taller than the other. So my alternative is just going to be two-sided, that the girls minus the boys is not equal to 0. I need to define my parameters. So I'm going to say that the mean of the girl minus the mean of the boys. I'm looking at the difference in mean heights of 10-year-olds. And I'm specifically doing girls minus boys. Okay, so that's my state. Let's talk about the plan. Okay, so it says in the problem, both samples are simple random sample. Okay, I guess I can put a SRS's. It also states that they are independent. I can assume the population is, so the population of girls is greater than, how many girls did I take? 12? I know the population of girls is more than 120, and I know the population of boys is more than 80. That I know. And then lastly is my normal condition. Since both populations are normal, I know the sampling distributions are normal as well. Okay, and so here I will say that I am going to proceed with, I've got a 2-sample situation. We already said that because we know the population standard deviations, I can use a z-test for means. Okay, so let's do this first on the calculator. I'm going to go into my menu, choosing tests. And this time I'm going to choose option 4, option 3, 2-sample z-test. And notice that it doesn't say that it's a z-test for means. It's just the one that doesn't have the word prop. Okay. I'm not given the actual data, so I'm going to choose the statistics option. Sigma 1, I'm going to use girls, so that's 2.7. Sigma 2 is boys, so I'm going to use 3.8. X bar sub 1 refers back to the girls, so that would be the sample value that I got for the girls, which I think was 57.2, so I can say X bar sub G was 57.2, X bar sub B was 55.4. So I'm just going to jot that down. Those are the values I'm going to put in here. So 57.2 for the girls, And the sample size for the girls was 12. And then for the boys, 55.4. And we only had a sample of 8 boys. Okay. And so then I'm doing a two-tailed test. And notice that it's not asking me whether or not to pool. If you are ever asked to pool, just make sure you say no. So I'm going to go ahead and choose calculate. And I'm given a lot of information. So when I go to write it down on my paper, we got to make sure that we write it right. So do, okay? Remember, we're doing a two-tailed test. So I'm going to end up with a 2 times the probability. The very first thing I write has to do with my sample results. And I'm looking at a difference between 2 samples. So I'm going to do x bar sub g minus x bar sub b. I'm going to actually have to compute that value myself. So I'm going to kind of leave that blank for a minute, and I'm going to go to the next step, which is stating my z-score. So it's going to be 2 times the probability that z. I'm going to look on my calculator, and I can see that the value of z is positive. So that means that the difference must be positive, and I'm going to use a greater than symbol. The z value itself is 1.159. And then the p-value for the test is 0.247. Okay. So the only other thing I need to fill in is this difference here. So I'm going to do that just by subtracting the 2 sample proportions, 57.2 minus 55.4. And that's the only thing your calculator doesn't do for you, and that's 1.8. So this we had to do ourselves, okay? So that's the do. Now, if instead you wanted to use your probability distribution to do that, I'm going to do the same thing that I did, except I'm going to physically have to compute my z-score. Well, let's think about it. If I were to compute my z-score, my z is going to be my observation minus the mean over the standard deviation. And if I've done this correct, and I haven't actually done this ahead of time, so I really do hope it works out, I'd be looking at taking 1.8 minus the mean. If I go back to my distribution, the mean is 0.7. And dividing by the standard deviation of my distribution, which we found to be 1.553. And if we have done this right, when I do that calculation, I should get 1.159. So let's hope for the best. Let's see, 1.8 minus 0.7. And when I divide, and now remember, I'm using rounded values, so the value might be a little tiny bit different. Crossing my fingers here. And I got something different. That's a little bit different. I'll have to go back and check on that. Okay, I figured out what I did. When we're standardizing, when we're going from this step to this step, and we have to subtract our observation minus our mean and divide by the standard deviation. The mean that I'm using here is going to refer back to my null hypothesis. And so if we refer back to the null hypothesis, what am I assuming to be true about the difference in means? I'm assuming that the difference is 0. So if instead of using my sampling distribution, if instead I put a 0 here, now when I do the calculation, if I do 1.8, obviously I don't need to subtract 0, and I divide by my standard deviation of 1.553, I will get that z-score again, that 1.159. Sorry about that. Okay, and so if I'm going to compute this by hand, then I would simply go into my second distribution menu. I would choose my normal CDF command. And since I'm doing an upper tail, I'd start, my lower bound would be at 1.159. My upper bound would be 9999999. The mean would be 0. The standard deviation would be 1. And when I go to paste, you're going to see that my p-value is 0.123. And that is different than this number because this number represents the two-tailed test. And if you're going to do it by hand, instead of using the test on the calculator, you will have to double it. And so you will see that obviously there's a slight difference because of rounding, but they end up being the same thing. So I know that what I did right here may have confused you. If you go back into your notes and take a look at The z-test statistic, if you look at these two computations, our null hypothesis is basically telling us that this difference is 0. So whenever we're doing a test of significance, this value is actually going to zero out. Whether we're using a t-distribution or a z-distribution, it's always going to zero out. So even though the sampling distribution may have a mean somewhere else, when we're doing a test of significance, we're always assuming that the difference in means is 0. Okay, and so the last thing we want to do is talk about the value that we get, that 0.24. And so here I would basically say that since my p-value of 0.247 is greater than any alpha value, suppose it's 0.05, I know the result is not significant. That's the first thing you want to say. Since it's not significant, we cannot reject the null hypothesis. Okay, now the very last thing you want to do is make sure that your conclusion is in terms of the alternative hypothesis and also in context. So basically what that means is we cannot, or we do not have evidence and now we're talking about a conclusion, not an assumption anymore. So we do not have evidence to conclude that there is a difference in the mean height of 10-year-old girls and boys. Okay, it's very important in your conclusion that you're talking about, that you go back and make sure you're talking about the parameter of interest, which was the difference in mean heights. That's important. You can't, sometimes people will just say that there is a difference, or they'll be talking about difference in boys and girls. You want to make sure that you're specifically relating to the measure. In this case, it's means. Okay, I want to talk about this special case of matched pairs data. So matched pairs, think back to some of the experiments we did, like the Pepsi challenge that we did, where each individual got to taste both Coke and Pepsi. In a matched pair situation, you may have two sets of data, but if the data is matched, so for example, if I'm doing before and after test scores, like a pre-test and a post-test, the two sets of data aren't going to be independent because they're referring to the same individual. So in a case such as this, we will look at the difference for each individual score and then take the average of the differences instead of the difference of the means. I know that sounds kind of silly, but there's a slight difference when we're dealing with matched data. With matched data, the two samples are not independent. So we don't have independence. So that means that we subtract the individual values, then find the mean difference. And so there's only going to be one sample of data. And so we're going to go back to the processes and the procedures that we used in Chapter 9. I'm showing you this now in Chapter 10 just because I think once people start to see two sets of data, they always want to jump into two sample situations. But let's take a look at this scenario. It says a company institutes an exercise break for its workers to see if this will improve job satisfaction as measured by a questionnaire that assesses worker satisfaction on a satisfaction index. Scores for 10 randomly selected workers before and after implementation of the exercise program are shown. The company wants to assess the effectiveness of the exercise program. So the question here is, why would it not be appropriate to use a two-sample test of significance here? And that's because each of these numbers is paired. They're linked together. I'm not looking at two different groups of people. I'm looking at one group of people, and I'm measuring them before the exercise program was introduced, and then again after. So the two sets of data that I have, even though I'm going to put them in two different lists, even though that's the case, they are not independent. So the first thing you do want to do in a situation like this is to go ahead and enter the data into lists. So I'm going to just go ahead and use list 1 and list 2. So go ahead and press pause if you have to and enter your data. Okay, once you've got the data entered in the calculator, what we want to do now is find the difference. And I'm going to do, let's see, we want to see if the exercise program is effective. I'm assuming that a higher rating means that workers are more satisfied. So I'm going to actually do L2 minus L1 because I would expect that if I subtract that way, there should be a positive difference. That might not be the case. Some people might be bitter that they're being forced to exercise at work. Who knows? So on my calculator, I'm going to go up to the tip top of list 3, and I'm going to go ahead and do the subtraction L2 minus L1. And you might find that some of the values are positive, some of the values are negative. And so what I would do then is just maybe jot down these numbers. So this is a -1. We've got 8, 21, -4, 11, 14, 15. And then if I scroll down, I'll get the rest of that. 15, and then we've got 6, 5, and 10. Okay, so we can see for the majority of individuals that their rate went up or their satisfaction on the index went up a little bit. Is it significant? I don't know. But understand that we would not want to use a two-sample test of significance here because the two samples are not independent. So we're going to want to go ahead and perform a test of significance that would be appropriate. And this goes back to using one sample procedures. Now, we're not given anything about the population standard deviation, so I'm going to need to use one sample t-procedures or t-test for means. And that's because in this case, we don't have any information about the population standard deviation. So I know this ahead of time, kind of going into it. So again, I'm only dealing with one sample. So my null hypothesis is going to be the mean is equal to, well, if I don't think there's any difference in the ratings, my mean would still be 0. I'm looking at a mean difference of 0 points, I guess. And the alternative, if I think that the exercise program is effective, the way I've subtracted, I would expect that mean difference to be positive. But now let's make sure that we define mu, because this is going to be really important. Mu represents now the mean difference in satisfaction ratings. Be really careful, because in the last test we did, it was the difference in means, where I actually subtracted, I took the mean of both groups and I subtracted them. Here, I subtracted first and then calculated the mean. So it's the mean difference in satisfaction ratings. And I did after minus before. And so I'm just going to go ahead and indicate how I did that subtraction. So let's talk about our conditions. We're going back to what we did in Chapter 9. So this is just using the one sample procedures. My conditions, would be simple random sample. So do I have, is this group of individuals a simple random sample? Does it say? It says randomly selected. Perfect. Okay, the second one, I'm going to have to assume that the population of employees is greater than or equal to 10 times my sample size, or 100 employees. Okay, and lastly, this is my normal condition. I'm not told anything about the distribution of scores on the satisfaction index, so I have no idea if it's normal. Obviously, my sample's really small, so this is a situation where I have to construct a normal probability plot. Now, I'm only doing the normal probability plot on the data that I'm analyzing, which is in list 3. So when I go into my stat plot, I'm going to make sure I turn it on, and I'm going to choose my normal probability plot option, which is the last graph, and I'm going to change my list to list 3. Now, if I was using two sample procedures, I'd need to do a graph for both sets of data, but since I'm only interested in the difference, I can go ahead and just choose list 3. And then I'm going to go ahead and zoom 9. Okay, and I can see really clearly, whoops, it looks like I have a graph in there, so let me just clear that out. All right, when I look at that plot, I can see pretty clearly. In fact, I'm going to take a snapshot because I can, instead of drawing all those little dots. Okay, so there's my normal probability plot. So this tells me that the data is distributed approximately normal. Now remember, this is not my population. it's not even a sampling distribution. I am just saying that my sample data is distributed approximately normally, and now I'm going to go ahead and proceed with my one sample t-test for means. So now I move to my do phase. So my do phase, I'm going to be looking at the probability that x bar, I'm assuming it's going to be greater than some number, and then I'm going to standardize it to be, this time, a t, and then I'm going to have a p-value. My degrees of freedom in this case are going to be 10 minus 1 or 9. If I was using a two-sample procedure, the calculator would spit out the degrees of freedom that it used, and it wouldn't necessarily be a whole number. So let's go ahead into my tests. I'm going to go, this time again, I'm just doing a one-sample t-test. This time I am using data. I'm not interested in the individual data in list 1 and list 2. I'm only interested in the distribution of the differences in those values. My null hypothesis is 0. Again, my data is in list 3. It's a frequency of 1. You're not going to have to change that. And I expect my alternative hypothesis to be greater than 0, or greater than the null. Calculate. All right, let's see. X bar in this case is 8.5. The t that I'm given is 3.597. And my p-value is 0.0028 or 0.003. Obviously, that value is significant, which means that I can reject my null hypothesis. There is evidence that there has been an improvement in the satisfaction scores. Now, I do want to make sure that I'm going back and stating this in terms of the parameter that I've defined. So I would want to say, let me actually write this out so that you guys are saying it properly. So since p equals 0.003 is less than alpha of 0.05, the result is significant. We can reject the null hypothesis. Oops. We have evidence that let's go back to how I defined it, the mean difference in satisfaction ratings is greater than 0. Now, let's put that in layman's terms. Thus, or meaning, satisfaction has improved since the implementation of the exercise program. Okay, that's all I'm going to write. Okay, and so that would be putting it into context. Okay, so I hope that kind of helps lay things out for you. I'm going to stop there. And so in class, you're actually going to do some problems together. The homework that I normally would have assigned this evening, or for this that's associated with this lesson, you're actually going to do together in class. And then when we see each other again, we'll start working on a review of the chapter and hopefully answer any questions that you have that are remaining. So I hope this was helpful. Make sure you come with questions if you have them. I'm not going to be in class on Thursday, but we'll go over them as soon as I get back.